So in this series of videos, we're going to be looking at how we find area when we're working with polar functions. So we know that we can use integrals to find area of rectangular functions, and that those are all based off of rectangles. It's going to be a bit different with polar functions because polar functions aren't based on rectangles. They're based on arcs or on sectors of circles. So first off, we do need to have a brief review of how polar functions are graphed. On the AP Calculus exam, they typically give you the graph of the polar function, or you have your calculator available that you can graph it on your calculator. But regardless of whether a graph is provided or you look on your calculator, you need to have a sense of how to read a graph of a polar function, because a lot like parametrics, the order these are graphed has a bearing on this. So remember, the idea here is, even though we're on the xy plane, we're starting with a theta of 0 at the positive x-axis, and we're moving counterclockwise until we get our entire shape, which is typically either going to be pi or 2 pi to get our entire shape, but not always. So I like to plug in values that I know. So, 0, pi over 2, pi, 3 pi over 2 are nice to plug in to get a sense of the radii. So if theta is 0, the r is going to be 2 times 1, and cosine of 0 is 1, so 2 times 2, which is 4. So when theta is 0, I have a radius, so from the origin, I'm going 4 with a theta of 0. So this is where I'm starting. If I then say theta is pi over 2, well, the r is going to be 2 times 1 plus cosine of pi over 2 is 0. So I get 2. So at an angle of pi over 2, the radius from the origin is 2. If I say theta is equal to pi, r is going to be 2 times 1, and then cosine of pi is negative 1, and I get the radius is 0. So even though my angle is at pi, I don't move any distance from the origin, so I'm still at the origin. And then if I say theta is 3 pi over 2, r would be 2 plus 1, or I'm sorry, times 1 plus 0, which is 2. And then if theta is 2 pi, I get 2 times 1 plus 1, which is 4, and I end up back where I started. Now, if you want, you can throw other common angles in, like pi over 4, 3 pi over 4, 5 pi over 4, etc., or pi over 6, or pi over 3. Those are also nice ones to throw in. But in this case, I know I'm starting here when theta is 0 and the radius is 4, come around to here. I know to get from a theta of pi over 2 to pi, I know I have to go into the second quadrant, but I have to approach the origin here when theta is equal to pi. Then I come back around, and we get a shape that looks a little bit like a heart, which is why we call it a cardioid. But the key here is, as we are doing this, we are measuring from the origin to our different points. And if we think about it, what we're doing is we're opening up our shape like a fan, like those small handheld paper fans that you spread open. And as I keep going around, it's spreading out like this. But if you notice that when I look at graphing like that, I am not graphing it based on rectangles. I'm graphing based on sectors of a circle. So if we can find the sector of each of the area of each of those sectors and accumulate them, we get the area of our that's inside our polar graph. So we actually have a formula for this. It's based off of areas of sectors. This video is just not the place for us to go super deep into where this is coming from. But if I want to find the area between the origin and the polar curve, and please note, it's between the origin, not the x-axis, the origin and the polar curve. It's the integral to accumulate all these little tiny areas of 1/2 times r squared. The pi that you would expect to see comes from the angles as we do the antiderivative and plug in upper bound, plug in lower bound. So an example of this, if we look at the graph I just made, so here graph is provided. I want to find the area of the region enclosed by r equals 2 times 1 plus cosine theta. The first thing I need to figure out is what are my bounds. So I need to get a sense of where am I starting, where am I ending. So I do it by just taking this and saying, okay, if theta is 0, all right, I start here when theta is 0. Pi over 2, r would be 2. So here's where I am at pi over 2. Here's where I am at 3 pi over 2. I'm sorry, at pi. Here's where I am at 3 pi over 2. And then I'm back here for 2 pi. And since I'm filling in my area like this, that's how I fill in my areas. I get kind of a palm frond effect there. I do want to go all the way from 0 to 2 pi, and then 1/2 times whatever my r is, squared. And this is with respect to theta. And typing that in my calculator, what I end up getting is an area of 18.850. Now, we can get other shapes, or we could be asked to find areas of just part of the region. So if I want to find the area inside the inner loop of the limison, hold on, correct my spelling here, limison, r equals 2 sine theta minus 1. Remember, I'm not going to be filling in my loop here with lines all going the same direction. I'm filling them in like I'm fanning it open, like a palm frond or like a fan. And I need to know then, okay, where my angle's at there. So I start with saying, well, if theta is 0, r is going to be, well, 2 times 0 minus 1, it's just -1. So here's where theta is 0. If theta is pi over 2, r is going to be 2 minus 1, which is 1. So here's where I am at pi over 2. Okay, so somewhere between 0 and pi over 2, I start that inner loop. Well, I notice the inner loop is at the origin, so my radius has to be 0 when I start and end the loop. So I need to solve for theta to find out when I'm going to start and stop that loop. And so the loop starts and stops when the sine of theta is 1/2. So I think to myself, okay, what angles have a sine of 1/2? Well, pi over 6 has a sine of 1/2, as well as 5 pi over 6. So that's actually pi over 6 is when I'm going into the loop. So that's pi over 6. And then I go to pi over 2, and then I come around to the origin again, and at 5 pi over 6, I'm back at the origin. So that tells me that for my bounds, I'm going from pi over 6 to 5 pi over 6. I have 1/2 times my radius, 2 sine of theta, minus 1 squared with respect to theta. And when I put this in my calculator, I get that the area is 0.544.